Hi, welcome back to Financial Engineering and Risk Management. Today we're going to talk about conditional expectation and variances. So let x and y be two random variables. The conditional expectation identity says the expectation of x is it's just a nested expectation. Expectation to x given y. So what is this thing? This thing is a function of y. So let's just say g of y. So basically it's expectation of x given that y is a y. So basically this is partitioning y into the set of all possible values. So basically we're taking this expectation over x, so assuming that y is y, what is the expectation of this x? And so this is a function of y. And then we take the expectation of that over all y, and that's how we end up with expectation of x. And the conditional variance identity says this: variance of x is variance of expectation of x given y plus expectation of variance of x given y. So again, if y is partitioning, if y partitions the space into a set of possibilities, this is just an example. Like let's just say there's three possible values for y, like y1. Here y2, y3. So then the variance of x is, so this expectation of x given y, this is what is within here, what is the expectation of x given, and then what we do is once we find this, then we find the variance of these three numbers. Okay, so that's this first term. For the second term, we're going to take the variance of given y equals y. What is the variance within this? So we're going to take all the x inside here, and we're going to find the variance, and then we're going to take the x. We're going to average that out over all three subsets. So as if it sort of makes sense in your mind, so the variance of x as a random variable depends both on both on like within or like how the variance differs across these sets, and also within a set the average variance. So hopefully that makes sense. A random sum of random variables. Let w is x1. So you can see I already have some little doodles here. Let w equals, am I still recording? Yes. X1 plus x2 plus dot 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 plus xn, where the xi are IID with mean mu and variance sigma squared, and where n is also a random variable independent of the xi's. Question: what is w? So what was kind of tripping me up here a little bit is that the number of terms here depends on n. So I know about linearity of expectation. I know that the that the sum of a bunch of variables should be, I don't know. I think I can prove this easily. But the point is, due to linearity of expectation, we can bring the e inside. I need to review this later. And then this is sum of xi, given n. And so this the n xi is independent of n, so this is just equal to mu, and there's n of these terms, so therefore it's equal to n mu. So you can see this is, as promised, this is a function of n. And then we can take the mu out, and we end up with mu en. Okay. And then the variance of w, to compute this, we use the same formula, and we can bring in the mu, we can bring this result into here. And for this, the way the professor explained it was that it's the variance of a bunch of identically independent random variables is equal to n times the variance of, and they all have the same variance, is equal to the variance of one of them. That was just sigma squared as given, and so then we take the sigma squared and we get that. Okay. An example: chicken and eggs. A hen lays n eggs, where n is the last slide. Yes. Where n is approximately Poisson. Each egg hatches and yields a chicken with probability p independently of the other eggs in n. Let k be the number of chickens. What is expectation of k given n? So then the way we're going to, so k be the number of chickens that have been laid, okay, from the eggs. So I guess what we do then is we can write k as a sum of random variables, 1h. So this is an indicator function from I equals 1 to n, where 1h is 1 if ith egg hatches, and 0 otherwise. And then the expectation of one of these IH is equal to P, because the probability P it hatches, probability 1 minus P it doesn't hatch. So then again, with linearity of expectation, we bring the expectation in here, we get summation, and we end up with this is equal to NP. And then we put that into here, and we take the expectation. The P is a constant, it comes on out, expectation of N. As given, it's Poisson, so this is lambda P. So as the professor explained, that also sort of makes logical sense. If you have N eggs in the beginning, and they're only, according to a Poisson distribution, on average, lambda, yes. Let me think. I guess n lambda. Some of them are gonna hatch, right? Oh no, sorry. N is Poisson, so the expectation of n. N eggs. No. This n varies according to the Poisson distribution. So, No, n is a random variable. It's not a number, so I'm getting that wrong. So on average, this is lambda, and then p of them hatch, so that's why it's lambda p. So you can just realize that that's about what it looks like. Okay, thank you very much. See you next time.